So today we're going to transition from graphing linear equations into looking at graphing linear inequalities. The inequalities that we did in Unit 1 only had one variable. And so for those inequalities, we graph them on a number line. The inequalities we're going to look at now are two variable inequalities, meaning I have both an x and a y value. So I can't use a number line to graph that. I need our coordinate plane where we have our x and our y. So first thing I want to do, so it says check whether these ordered pairs, and it lists a bunch of ordered pairs, are solutions for this inequality. And we'll do that in a minute, but before we look at that, I want to go ahead and just graph the line. Okay, so not an inequality, just here's a line. We've been doing this for a while now. So to graph this line, I'd subtract 3x. And I'd say, okay, my slope is -3/1, and my y-intercept is at 0, 2. So I can graph starting with my y-intercept, rise over run to get another point. Maybe I'll get a couple of points just to be safe. And I'm going to graph just the line. Okay. So there's my line, y equals -3x plus 2. Okay. So now we're going to go through, we're going to substitute these ordered pairs into the inequality. Notice the inequality is the same as the line, but the equal sign was replaced with greater than or equal to. And it says, and plot the result on the graph from step 1. So I'll explain what that means as we go. So first, let's look at 0, 0. If I plug 0, 0 into the inequality, it's going to make all of this 0. Is 0 greater than or equal to 2? No, right? 0 is not greater than 2. This is a no. So I'm going to, on my graph, where 0, 0 is, I'm going to just put an X. And I'm putting it in orange. That point did not work in my inequality. So there's our first check. Now I'm going to look at 2, 0. If I plug in 2, 0, so 2 for X and 0 for Y, it gives me 6 plus 0, or 6 greater than or equal, not to 6, to 2. That point would work, right? 6 is greater than 2. So for that point, 2, 0, 2, 0, I'm going to just put the point and I'm going to put it in blue. Okay, that point worked. This one did not. We're going to look at another point. Let's look at 4, -1. I'm going to plug in 4 for X and -1 for Y, which gives me 12 subtract 1, or 11. 11 is greater than or equal to 2. That works. So I'm going to, in blue, plot 4, -1. That point worked. And now I'm going to continue checking points on the other side here. So I want to check 5, 2. 3 times 5 plus 2, is that going to be greater than or equal to 2? That's going to give me 17. 17 is greater than 2, so I'm going to go 5, 2. This point worked. Let's look at -1, 1. So 3 times -1 plus 1, is that greater than or equal to 2? That's going to give us -3 plus 1, or -2. -2 is not greater than +2. That one does not work. So at the point -1, 1, that did not work. And our last ordered pair, -2, 4. So 3 times -2 plus 4 greater than or equal to 2. This would give me -6 plus 4, or -2. -2 is not greater than or equal to 2. So this point, -2, 4, -2, 1, 2, 3, 4, did not work. So now I want you to take a moment and look at what happened. So here's my line. Here are the points that worked. Here are the points that did not work. And what do you observe? What you may observe is that all the points that worked, all the points that were solutions, were to the right of the line. Okay, if here's my line to the right of the line, that's where my solutions were. And all the non-solutions to the left of the line. So in fact, this is something that's always going to happen with our linear inequalities, our inequalities that have two variables, where we will have a line in one half of the graph will include the solution. So all of this area, any of these points would be a solution to that inequality. And on the other half of the graph, all of the points over here would not be solutions. Okay, so the line that we drew kind of broke my coordinate plane into two half planes, okay, where one half includes all the solutions and the other half does not. And so we're going to get some clarity on how to decide where my solutions are and where my solutions are not, and what a graph of an inequality actually looks like in the next few examples. So notice that the actual line piece, the graphing the line piece, was identical, okay? And that's always going to be true. So when we're graphing an inequality, we're going to start by drawing what I call a boundary line. So we're going to draw in the boundary line. And we do that by rewriting into y equals mx plus b. And then we decide, and we haven't talked about this piece yet, and we will in a minute, we decide if it should be, if it is included or not included. Included is a solid line. Not included, we would only draw in a dashed line. And this will be new info to us today. And we're going to talk more about that in a minute. But sometimes we'll draw our line just like we've always drawn lines. And other times when we draw on that line using slope and y-intercept, we draw in a dashed line. And it depends on the inequality. And the same idea with open circle, closed circle when we were graphing on a number line, or parentheses versus brackets when we were writing interval notation. Okay, so we rewrite into y equals mx plus b, and then we use m and b to graph the line. Okay, so not inequality, but just the line. And then the second thing that we need to do is we need to determine where to shade. Okay, so one half of my graph will always have my solutions. And so to do that, we are going to test a point. If the point works, if it is a solution, then I shade the side to include the test point. If I test a point and it's a no, it's not a solution, then I shade the opposite half of the graph. And again, I know this is new content today, so we will talk about all of this as we continue to look at inequalities on the next page. So now let's talk about a few of the specifics with this new idea of graphing the two variable inequality. So just like when we were graphing on a number line, we had non-included inequalities and included inequalities. So non-included inequalities means when it's just listed as less than or greater than, and it doesn't include the actual line or before the actual value that we were talking about. It's just values either greater or less than that. Okay, if we have just less than or greater than, then when we draw in our boundary line, we will draw in a dashed line. So for example, here's my XY axes. I'll have a dashed boundary line that I'll draw in, and then they'll be shaded. It'll be shaded on one half or the other. And so what that means is that where it's shaded would be solutions to my inequality. And on the line, the points on the line are not solutions. Okay, meaning the line is not including solutions on it. It's just creating a boundary between solutions and non-solutions. If I have an inequality that's less than or equal to, greater than or equal to, that's when we draw, as we did on the first example, a solid line. So here's my graph. Here's a solid line. And I'm going to have still some shading on one half or the other. And when I have a solid line, then still these are solutions wherever I've shaded, but my line also contains solutions to the inequality. And so an inequality is different than an equation in that an equation is only when it equals a certain value. That's why we are limited to just the line. Here, it's equal to that certain value or less than, or equal to that certain value and greater than. So when it includes that equal to, all the points on the line are solutions to that. And then what other half includes the other solutions where it's either less than or greater than that value. When it's just less than or greater than, this is just creating a boundary, but I don't include the points on that line. And I think you'll get some more clarity on the examples that we do, okay? So graphing my inequality. So first, now this is the tricky piece. First, what I do, because I don't want to worry about, this is also why I test a point. Because remember when we multiply and divide by negatives, and there's all sorts of things that we need to be careful of in terms of flipping our sign with an inequality. So I kind of avoid all of that by using the steps that I'm going to teach you to use. So the first thing I'm going to do is rewrite the line. Notice I'm not putting inequality, and y equals mx plus b. So I'm going to take my inequality exactly how it is, but instead of writing greater than in the middle, I'm going to write equal to, because I just want to look at what does that boundary line look like, okay? And so I'm going to subtract 2y, and that would give me y subtract 3 equals negative x. And I'm going to add 3. Okay, so here's my boundary line. It's going to have a slope of -1 and a y-intercept at 0, 3. Now, before you go crazy graphing this, we need to think about the fact that it's an inequality. So because it's an inequality, I need to look at the inequality sign and say, oh, because it's just greater than, when I draw on this line, it should be a dashed line. So I'm going to go to 0, 3, slope of -1, get a few points, meaning the points on this actual line that I'm going to draw in are not solutions of the inequality, but it's going to create a boundary between points that are solutions and points that are not solutions. I'm going to draw in a dashed line. Okay, so there's my boundary line dashed because of the type of inequality it has. I rewrote it, looked at slope and y-intercept. Now I'm going to test a point. Now you can test any point that's to the right or left of this line. What you can't do is test a point that's on the line. I try to test 0, 0. So as long as my line's not hitting 0, 0, I can use 0, 0. And the reason I use 0, 0 is it makes it easy, because anywhere there's a variable, it's just going to get zeroed out. So if I plug in 0, 0 to the original inequality, okay, so I'm not going to plug in 0, 0 here in case I rewrote that wrong. Okay, I want to go back here, and I'm just going to, and 0, 0 makes it easy. And I wouldn't even typically write all of this out, okay, because anywhere there's a variable, it all just becomes 0. So I get -3 greater than 0. When I plug in 0, 0, that's what I'm left with. Is -3 greater than 0? No, it's not. Okay, so this does not work. This is a no. So I should shade the opposite half, meaning here's 0, 0. Here's the point I just tested. Okay, this point did not work. That means this is not a solution. That also tells me that all the points on this half of my graph are not solutions, and that my solutions must be on this half of the graph. Really, I should use a colored pencil to shade because that's pretty hideous. Okay, but every point over here, any point I grabbed from over here should work in my inequality. This is where my solutions live, and expanding out this way, okay? It's unbounded, going infinitely in this direction. Those are where my solutions live, okay? Let's look at another one together. So here we have 5x subtract 2y is greater than or equal to 6. So this time, looking at this inequality, I know I should have a solid line because it is greater than or equal to. I'm going to take my inequality and write it as an equation so I can get a boundary line. And I'm going to rewrite that equation in y equals. And then I know I have a slope of 5/2 and a y-intercept at -3. So I go 0, -3, rise over run of 5/2. Because of the type of inequality it is, I know to draw in a solid line, or that all the points on that line are also solutions. Okay, now I will go ahead and test 0, 0, again in the original inequality. So 5 times 0 minus 2 times 0 greater than or equal to 6. That zeroes out everything. Okay. 0 greater than 6? Nope. Okay, so here's the point 0, 0, by the way. That's the point we tested. Didn't work. Okay, so I should shade. This is where my non-solutions are. I need to shade where my solutions are, which would be on the other half of the graph. Okay, now you may be thinking, well, like up here, it was greater than, so it's above the line. Well, this is also greater than, but it's below the line. Why is that? Okay, because kids kind of get caught up on, well, below would be less than, above would be greater than, and that is actually correct. The reason it's not true for this particular inequality is because if I had rewritten this into y equals and left the inequality sign, I would have divided by a negative, which means this inequality would have flipped and it would have been less than, which is why we're shading below the line. So in terms of greater than, less than being above, below, that is correct, but we have to keep in mind that signs flip sometimes if we divide by a negative. So that's why it's safer to just quickly test a point than it is to assume above, below based on the initial inequality, because that sign could have flipped somewhere when we rewrite it. Okay. So now on the next page, there's 4 inequality graphs. So I'm going to give you a moment. We'll do 2 and 4 totally. You'll do them totally on your own. For 1 and 3, what I want you to do right now is I want you to just graph the line. So I want you to rewrite the boundary line in y equals and just graph the line. And I'll do it kind of quietly on my own while you're working. And be thinking about, should I graph a solid or a dotted line or dashed line? Okay, so for both of these, just graph the line. We'll talk about shading in a minute. Okay, so on the first example, I know I should be graphing a solid line, or that these points are also solutions to the inequality. And rewriting my line, I have a slope of -1/4 and a y-intercept at 0, -3. Okay, now if I looked at, so here's 0, 0, right here. If I plugged in 0, 0 to my initial inequality, and so like I said, I don't always write all of this up. 0, 0 is just going to zero out all of this. and I'd be looking at 0 is less than or equal to negative 12. Now 0 is not less than negative 12. That's not true, which means that this is not a solution, and my solutions would be on the other side of my boundary line. Okay. Now on 3, when I went to graph the boundary line, so I have a y-intercept at 4 and a slope of 3, I couldn't go up 3 over 1, so I went negative, negative, and I still, you can see, have a positive line here. Let's test our point 0, 0, and if I plug that in, it would zero out that side totally, and it would give me 0 is greater than negative 4. 0 is greater than negative 4, that's true. So because this point is true, that means that's a solution. That means all of my solutions must be on that half of my graph, on that side of my boundary line. Okay. So now I'm going to pause the video totally and let you do 2 and 4 completely on your own. So let's look at 2 and 4. First of all, you want to check several things. So did I have the right slope and y-intercept? Here's my graph. Did I draw a solid line? Because that's what the inequality indicated I should do, that it was an included inequality. And then testing 0, 0, it does not work. So I should shade the other side of that boundary line. On 4, same idea. Did you have the right slope and y-intercept? Slope of negative 6, y-intercept at 2. Did you draw a dashed line? Okay, did you take the time to observe what was happening here? This is a non-included inequality, dashed line. 0, 0 works, so I should shade the side of the line that has 0, 0 on it. So now let's look at one other thing that we will see, which are these Hoy and Vux lines, horizontal vertical lines, in terms of inequalities. So my inequality, x is less than negative 2. First of all, we know it should be a dashed line. And it is a Vux, a vertical line, where x equals that number and it has an undefined slope. So where x is negative 2, which is here, I'm going to have a vertical line that's dashed because of the type of inequality that I have. And for this, we can just kind of think about, well, where is greater than, where is less than? So where are my values of x less than negative 2? Well, right here would be less than negative 2. It would be x is negative 3, x is negative 4, and so on. So my values that are less than negative 2 would be to the left in this case, and I shade to include where less than would be. If I had tested 0, 0, it would have given me 0 is less than negative 2, which is not true. So I would shade the other half of my line. So I can still go through the procedure as up above, but it's a little easier to just think about where my value is less than negative 2 for x, and it would be on the left-hand side. Same kind of idea for our horizontal lines. So here we have a horizontal line. This is a solid line, and it is a Hoy. So horizontal line, y equals a number. So where y is 3, we're going to draw in that solid horizontal line. And the inequality is y is less than or equal to 3. Well, my values that are less than 3 would be below that line. Or if I tested 0, 0, it would work, and I'd shade to include it. Okay, so that's a horrible job shading that in. I kind of like colored pencils because really it shouldn't be as messy as I'm making it be. Okay, it should be a nice, pretty shading underneath that line. Okay, so now you go ahead and look at the last 2 inequalities in our notes and graph the horizontal or vertical inequalities, how they read. Okay, so let's see how you did. For both of these, they should be dashed lines, so check yourself there. They were both non-included inequalities. This is a horizontal line where y is negative 2 and its y is less than negative 2 shaded below. Vertical line where x is negative 2, values where x is greater than negative 2 would be shading to the right.